Welcome to the story of a true pioneer in physics. This slide, titled Architect of the Unseen World, introduces the legendary Dutch physicist Johannes Diderik van der Waals and his significant quest for understanding molecular reality. He is depicted in his distinguished portrait alongside a blueprint of thermodynamic variables, including pressure, P, volume, V, and temperature, T. Van der Waals revolutionized our understanding of the microscopic universe by considering intermolecular forces and molecular volume through his famous constants, A and B. He successfully bridged the gap between gases and liquids. Join us as we delve into the history of physical chemistry and explore how this visionary mapped the invisible forces that shape our physical world. Observe the great ideological schism of 19th-century physics, the divide between mathematical simplification and physical reality. On the left, we see the theoretical illusion of the ideal gas model, which treated particles as mere point masses occupying zero volume and exerting no forces on each other. On the right lies the physical truth championed by van der Waals. He recognized that real molecules occupy actual physical space and exert mutual attractive forces, fundamentally altering pressure and volume. At a time when many dismissed molecules as convenient mathematical fictions, van der Waals bridged this profound gap, providing the mathematical validation that proved these invisible entities truly exist. Genius often faces formidable barriers. This timeline maps how van der Waals bypassed the traditional academic gatekeeping of his era. Born to a carpenter in 1837, his working-class origins lacked the classical Latin and Greek training mandatory for university degrees. Instead, he forged an alternative path through advanced primary school, a teacher apprenticeship, and rigorous self-study. The turning point came with the 1862 Thorbecke reforms. The creation of the new HBS school system triggered a desperate shortage of science teachers, sparking a crucial legislative exemption from classical languages. Though initially limited to auditing as a free student at Leiden, this historic loophole allowed him to break through the systemic divide, ultimately securing his doctorate in physics in 1873. Welcome to the ultimate intellectual showdown of late 19th century physics, slaying the anti-atomist dogma. On the left stands the established scientific elite, proponents of energetics like Ernst Mach and Wilhelm Ostwald. Their stance: matter is completely continuous, dismissing atoms and molecules as unproven, unnecessary mathematical fictions. On the right stands the challenger, molecular reality. Johannes Diderik van der Waals boldly asserted that molecules are actual physical bodies. He argued that liquids and gases are not chemically distinct substances, but the exact same molecules interacting at varying distances. As van der Waals later recalled in his 1910 Nobel lecture, he was entirely convinced of their real existence, viewing them as an aggregate of tangible bodies and empty space. Let's dive into the mathematics that changed physics forever, the 1873 equation of state. Here, van der Waals elegantly modified the ideal gas law to account for the physical realities of matter. The first modification, A, divided by V squared, represents internal cohesion. Because molecules exert a mutual attractive pull on one another, they pull inward, reducing the overall pressure they exert on the container walls. The second modification, B, accounts for excluded volume. Since molecules possess physical size and occupy actual space, the real volume available for them to move is less than the total container. By extracting these constants from experimental data, van der Waals provided the world's first concrete estimates of molecular size and attraction strength. Let us examine the paradigm shift matrix, which systematically compares the classical ideal gas model against the revolutionary van der Waals real fluid model across 5 critical dimensions. First, regarding particle size, the ideal model assumes zero volume point masses, whereas van der Waals introduces a finite physical volume represented by B. Second, intermolecular forces shift from zero attraction to cohesive attractive forces represented by A. Third, the phase state transitions from distinct, separate phases to a continuous spectrum where gas and liquid share the same fundamental nature. Finally, these physical insights translate into mathematical corrections, the simple volume term V becomes V minus B, and the standard pressure term P is corrected to P plus A, divided by V squared. Welcome to the geometry of continuity, a visual representation of how thermodynamics maps the transition between states of matter on a pressure, volume, P-V, diagram. This graph highlights two fundamental features predicted by van der Waals mathematics. First, look at the loop within the shaded spinatal curve, an unstable region where, below the critical temperature, the math predicts the exact zone where gas condenses into liquid. Second, observe the critical point, Tc. At the apex of this curve. At and above this precise temperature, the physical boundary between liquid and gas completely vanishes. The two distinct states merge into a single, seamless, homogeneous fluid, beautifully illustrating the absolute continuity of the gaseous and liquid states. Let us explore a profound conceptual breakthrough, the law of corresponding states, 1880. Van der Waals realized that nature's diversity could be unified through elegant mathematical scaling in three distinct steps. Step 1 begins with the specifics, where standard thermodynamic variables, P, V, T, rely on unique molecular constants, A, B, that change for every substance, from oxygen to water. By dividing these by their substance-specific critical limits, Pc, Vc, Tc, we reach. Step 2, the scaling. This defines reduced variables, PR equals P divided by Pc, $VR equals V divided by Vc, TR equals T divided by Tc, effectively cancelling out those unique molecular constants. T. His leads to step 3, the universal. A single, overarching equation of state now applies to all substances in the universe, regardless of their chemical makeup. Welcome to the conceptual culmination of this journey, the aha moment. This slide beautifully illustrates how two distinct scientific epiphanies converge to change chemistry forever. On the left, we have the reality of molecules, the realization that matter is granular, specific, and possesses unique sizes and stickiness. On the right lies the law of corresponding states, proving matter is mathematically universal when scaled to its absolute thermodynamic limits. These two pathways converge into the golden hexagon, the continuous architecture of matter. Van der Waals did not just invent a formula, he proved the universe operates on a seamless, continuous framework. Gases and liquids are merely the same physical bodies interacting at different distances, allowing us to mathematically predict a substance's entire physical destiny. Every scientific triumph carries a deeply human cost. This poignant timeline, titled The Abyss and the Return, chronicles a devastating chapter in van der Waals' life. Following a golden era of global acclaim between 1873 and 1880, tragedy struck in 1881. The untimely death of his 34-year-old wife, Anna, left him a widower with 4 young children. Paralyzed by grief, he entered a 10-year hiatus with 0 publications. Yet, the story does not end in the dark. In 1890, he made a triumphant return to science to address a critical weakness in his theory. This sparked the discovery of pseudo-association, the insight that molecules under pressure form temporary, non-chemical clusters as they transition into liquids. Welcome to the ultimate validation of abstract theory, the domino effect of discovery. This slide maps out the brilliant historical chain reaction triggered by van der Waals' breakthroughs. It begins with the theoretical foundation of 1880, where the law of corresponding states accurately predicted the extreme limits required to liquefy previously impossible gases. This acted as a literal map for cryogenic engineering between 1898 and 1908, enabling James Dewar to liquefy hydrogen and Heike Kamerlingh-Onnes to liquefy helium. Finally, this technological leap succeeded in unlocking quantum physics in 1911. Using liquid helium as a coolant near absolute zero, Kamerlingh-Onnes discovered superconductivity, proving that abstract thermodynamic theory directly birthed our modern high-tech era. Welcome to the intergenerational tree, a testament to a legacy that shaped the Second Dutch Golden Age of science. Appointed as the first physics chair at the University of Amsterdam in 1877, van der Waals did not just discover laws, he cultivated minds. His influence branches out through four remarkable figures. First, Diederik Korteweg, his premier PhD student and co-discoverer of the KdV equation for solitary waves. Next, his brilliant mentor Willem Hendrik Keesum, who mapped dipole-dipole forces and advanced helium liquefaction. The legacy then turns familial. His son, Johannes Diderik van der Waals Jr., who succeeded his father's physics chair, and his cousin, Johan van der Waals, a brave World War II resistance courier who later co-developed the clathrate hydrate model. Welcome to The Taxonomy of van der Waals Forces, a definitive breakdown of the three distinct microscopic mechanisms that drive molecular attraction. First, we observe Keesum forces, discovered by Willem Keesum in 1921, which govern the permanent electrostatic attraction between polar molecules. Next, we encounter Debye forces, characterized by Peter Debye, where a permanent dipole distorts the electron cloud of a neighboring nonpolar molecule to induce attraction. Finally, we uncover London dispersion forces, mapped by Fritz London in 1930. Driven by instantaneous quantum fluctuations in electron density, these temporary dipoles affect all neutral molecules and scale inversely as r to the sixth. Together, this triad maps the invisible forces shaping our physical universe. Welcome to a stunning display of nature-defying gravity, the macroscopic reality of quantum forces. On the left, a gecko effortlessly scales a vertical surface in a remarkable act of macroscopic defiance. How does it achieve this without suction or sticky chemical glues? The answer is revealed on the right, magnified 10,000 times. Millions of microscopic hairs, called setae, on the gecko's toes create an immense collective surface area. This allows incredibly weak, fluctuating quantum attractions, specifically London dispersion forces, to multiply exponentially. Together, these cumulative van der Waals forces generate an attraction strong enough to overcome gravity, proving that invisible subatomic phenomena can directly shape the macroscopic world we see. Welcome to the ultimate recognition of a lifetime of discovery, the laureate of continuity. This concluding slide celebrates Johannes Diderik van der Waals receiving the 1910 Nobel Prize in Physics for his pioneering work on the equation of state for gases and liquids. We see a timeline marking his final decade, from the 1908 validation of his theory through helium liquefaction, to the 1910 Nobel triumph, and finally his passing in 1923. His immortal words remind us that he sought not just mathematical equations, but the absolute truth of nature. By transforming physics from a continuous illusion into a granular reality, van der Waals left an enduring legacy that bridged the gap between the visible and the unseen.